So, what we are going to talk about today. It's so simple and attractive to use clouds and to scale your production, to put your headache to someone else's shoulders. But you have to have a strategy for managing your costs. Then you scale in cloud, and you have a strategy how to prepare your applications, then you go there. And we'll look at these aspects of what you do. Then you migrate or then you tune what you do there. I work with a company named Belsoft. My name is Dmitry Chuyko. I am an OpenJDK committer, and we release and support our own distributions of OpenJDK and native image tooling that, by the way, by default power Spring and Spring Native, Spring Boot and Spring Native containers. Then you build them using standard tools working with Spring Boot. We contribute a lot to OpenJDK. That's why I'm talking about some OpenJDK related things today. But it doesn't just happen that I talk to someone, but people come to us, and one of our friends, not even customers, told us a very fascinating story. So his firm is a very, very large production in the US, and they performed a digital migration project. They migrated to the cloud, one of major cloud providers. And it was a very brilliant idea. Why should we manage our own on-prem server fleet when we can actually migrate to the cloud? And it was implemented very well. So developers developed that solutions, DevOps deployed it, and CloudOps supported. Everything works very well. Developers spent their budget for development. Then DevOps actually deploy all that services, very, very huge and multiple numerous clusters. And someone operates them, but someone else get the bills. And business was really surprised by the bill that they've got after some time in that cloud. Then they had the auto-scaling working, and it was quite unexpected for them. So what was the problem? Well, actually, everyone did their work, except no one really cared about cost reduction in that pipeline. So developers stayed in some zen, actually performing development tasks, preparing business logic for production, but they didn't really care about what it costs to run it there or what it costs to scale it there. We already know that, of course, Java became container aware. If you use recent updates, even of Java 8, you got very nice containerization support there, and your applications works fine. But you still have to do something to tune them. You have to tune your JVM, or you tune your containers. You have a very plenty of options what to do there. And what really happens is that the resources are very often spent inefficiently. We'll see some reference to statistics, but it really happens. It's very common. It's not an exception. And when we talk about some efficiency, in the end, it should be numerically expressed. Well, you put some objectives, right? And then you turn that objectives into some measurable metrics. And that's a relationship between what SRE does and development and FinOps. And here, the key point is involving developers into the process of cost reduction and optimization related to their services. So when they define requirements, we enforce developers to work on having them actually satisfied. And that involves JVM tuning, that involves performance testing, profiling, and other related tasks, technical tasks that help to achieve that. So if the goals are not met, what should we do? Well, we must profile the application. We should figure out what really happens, what prevents our applications from meeting the requirements. In some cases, we have to redesign the entire architecture to meet them, right? Because how the system is designed also influences of how it works. So then we define that requirements. First, we have some business requirements like, well, we have to survive Black Friday, right? And exact, objectives, technical ones, are related to having a certain latency or certain availability during that exact days of certain load. And that means measurement of very well-known indicators, like is the system up, or how long does it take to respond to a request, right? So we take some measurement indicator. We have some condition that involves some indicators, maybe that can be a combined one, and that condition helps to reach the actual goal that we have, because we write code that powers actual business. So that objectives can be distributed across multiple services. So we have relationships between different services and other components of our systems, like message buses or data storages or file storages or whatever. It may be some physical systems may be involved. And there we can capture all the metrics that we love, as we can treat them as performance metrics, including uptime, quality of service, different times related to requests and responses on the client side, on the server side, in the different segments of response chain, or the final time that user of our systems, or maybe not a user, but some automated consumer actually observes. And all these metrics are related to what JVM does, because JVM does garbage collection, for example, right? And that immediately strikes your latency, because if you have stop the world pause, well, JVM does not respond, and this particular instance has a delay in response in all its clients. So as well, the same works for peak performance, because it depends on how good is the quality of your compiled code, if it's just-in-time compilation, or again, performing the compilation may be delayed, or something may happen, then you have a bailout and different compiler, like server compiler does not compile your hot method, etc. So we have two goals. We should meet our service level objectives, and we must reduce our cloud bills, right? So do more with paying less, but we actually do both, but wrong both. We can pay more and still break some SLAs and SLOs. Well, how does it happen? For example, we may underutilize our hardware resources. And again, as I said, it is a typical case. And it is scary how many resources we underutilize. So You saw previous talks about making greener solutions to fully utilize CPU and other resources available to you in the cloud or on-prem. But in real practice, a lot of resources are not used. Like 2/3 of what we have are used inefficiently. That's a huge part of the world resources that we have for our tiny computations. Well, this is not something that happens only in computer industry. The same company that provides us with cloud computing resource also delivers actual mail with some goods. And if you're lucky enough, you will have something like this displayed on this picture. And it is the very same situation. And what's even better, there is a direct analogy in the world of containers, right? Because you see containers here, you see standard shipping boxes. And it's more convenient not to think about effectively packing your carrot seeds together in a single shipping box instead of putting each one in its own one. Well, if someone would have a target, a goal to improve efficiency here, it could be made easily, right? So the same happens with your computing resources, with your I/O, with your CPU, with memory. So what should we do? First of all, we look at containers, right? Containers allow us to do many nice things, but JVM has to understand, and you understand how it is packed in the container environment, and you have to understand what's your environment and what JVM does there. So JVM has ergonomics, and that ergonomics change. They depend on what resources do you have, what it is. In container, JVM determines available memory, for example. And based on that, it can change the default garbage collector. But you may think of changing it yourself if you still see that it is more efficient, for example, to use serial GC. Even if ergonomics say, well, G1 will work better for you, but you have to capture that moment, then it changes, and what choice is best in your case. For the most basic ones, we can regulate the usage of memory in the container, right? And usage of the number of threads that we'll use for garbage collection, for default thread pools, for compilation, etc. And there are options that change several ergonomic behaviors, like acting as a server class machine. And still, even if you use very, very cheap instances, you will have, in many cases, you will have multiple threads performing some groups of tasks, like cheat compilation. So it won't make your JVM a single threaded by default, and it's even not possible at all. And still, there are all the code that does synchronization, even if you have a single CPU. That's important to understand. You have some trade-offs that especially hurt you if you have a single or kind of less than one CPU case. So when we put these applications in containers, we monitor that containers, we monitor our production, our clusters, and we also monitor our applications still as if they were not in containers. We capture GC logs, we analyze what happens inside our memory, what occupies memory, which parts of it are really hard. And some resources just work differently. Like shared memory may hurt your performance, right, if you use containers, or the lack of entropy, same. And remember, then we prepare that applications to run an application to run in a container. The typical case that is 99 point, I don't know how many nines after the dot, is a single application in the container. So that's the purpose of using the container. So why should you leave any gap unused? And you have underutilized environment if you leave some gap for someone who is not present there. Your application is a single user of that container, single consumer of its resources. And there are systems that help to orchestrate containers, to deploy them, to manage how applications communicate with each other, how they form the entire network that delivers some business functionality to users. But then they create clusters. There are still JVMs in it. And we configure those parts of the cluster to have some resources based on what we provide during the deployment. We have some requests for our applications, and then finally we put some limits, and Kubernetes, for example, schedule our apps to actual pods running on a physical hardware. And we have running code, we have scheduling. After some configuration, our code starts working, and then this scheduling happens, right? It uses requests that we created to place our code on the best suitable pod that it has. So it's a kind of soft limitations written that advise what available resources can satisfy this application. And there is also a CPU limit that's used to balance pods, right? Then they run on the node. And the node CPU resource is shared between them. We also have memory limits. And memory limit consumed by the JVM, then it runs within the container having that limit, is used to set, using some ergonomics, to set the heap size. And we can also provide flags that will derive our heap size based on our limit. But sometimes, and I heard that stories, people just set their heap size larger than the memory limit on the pods that they have. Well, because applications still can work for some time, especially if it doesn't consume all its memory on startup. But it just starts to fail on this even a moderate load, because JVM thinks, okay, I have this heap limitation if I have this flag set, and I actually may use all that heap. But OM killer doesn't think so in the operating system, in the host operating system, and it just kills such a process, such a container. That's nonsense. So pods that we start are monitored, of course, and all that processes coexisting on a single node. They are processes in containers, but they are also node processes, and they coexist in that host operating system as its processes. So we have to be careful about that. And then the big thing happens. Finally, Black Friday starts, and we need to scale a lot of things. And it's a nightmare, right? Because, well, it's the time that generates the most painful bills. So we should think about our services and split them. For some services, we really have to scale horizontally, and some services we probably don't. Like less critical or just not heavy loaded ones, or some ones that we can scale by vertical scaling by throwing more resources into them and making them just good enough to not be scaled automatically horizontally. What interesting strategies can be applied here than we do horizontal scaling is, of course, step scaling. Then we consume more working nodes before they actually become necessary. Of course, that helps to struggle with relatively low latency of nodes creation in clusters and in clouds. And full pre-scaling, then we are getting ready for some well-known point in time, like Friday starts, and increase the number of available instances in advance. So still, we can walk an easier route, right? We can rely on the most simple way of scaling by using what big cloud vendors provide us as a ready-made solution as a service, right? That solution will work. It will just cost some money. That's probably okay, or sometimes it's not. And still, any kind of scaling happens based on some metrics, that indicators that I mentioned earlier. And in this case, the most typical metric, of course, is the number of requests that some pods receive. But we have to understand what's the line where we have to scale. And it's a point to determine, and we'll look at it. It also can be any other metric, right? We can introduce it as a metric, formally as like a Kubernetes one, as a metric server, and use the plugin to scale based on that metric, right? It's also possible. But probably, like, if you scale based on CPU consumption, that might be not the best strategy, because that means you use a lot of CPU, but doesn't mean that it's used wisely. Probably not. So then we go to dependencies between our components. Like, imagine you have a service that calls a database and several other services. And the database responds like 100 requests per second at max. Well, it would be too naive to expect your dependent service to respond with more to more requests per second if each of them requires a database response, right? So you have to scale your dependencies first, like to improve your database performance by splitting the database, sharding, and all that techniques. From the reverse, you can have an underutilized routes. Like, imagine again a database that can handle like many requests per second, and it has only one consumer, but you can actually multiplex several users of it to utilize its resources effectively. And you have to look at metrics of your to look at your utilization, know performance of your dependent systems like databases, etc., and to use them effectively. So we still have underutilization, and we'll look what we can do to squeeze more out of our service and how we throw them into that cloud, right? So we start from classics, well, not even from R2DBC as that was covered in previous talks, but we'll start from classical Tectonic JPA Spring Boot sample. And it's a relatively small application that is built as a 40 megabytes jar, and if we create a native image out of it using Spring Native, it's like 124 megabytes. And then I ask, and my colleagues ask developers, what do they actually use to create containers? How do developers do that? Still, a lot of people create Docker file manually. But there are other options, like using Google G plugin or using cloud native build packs. So other interesting options include kind of something that we desire to treat as a magical tool, right? Someone please take our application and turn it into a working container. Well, you might think of some tools being tools of that kind, but that's not true actually. Like two ones listed here, Azure as, then you can containerize your application, but that's actually, I think, to let it work in that particular cloud. So you have still to provide the Docker file. So there's no magic, right? You have to work out your Docker file somehow. Another one is app2container from AWS. This tool tries to replicate your environment where your application runs, tries to analyze it. What operating system is it? What's the version of Java, etc. To keep things same as possible, but wrapped in a container. That's a wise approach, but still there's no magic. You have to tune that application, and it just helps you to deploy it in the particular cloud to get rid of the boilerplate. So you see, app2container, right? It just prepares some inventory for you, and there you have to decide what options to select and what ports, what requests you should put for that application. You have to provide them. So you'll have to write your YAML file or whatever, having that limits. Having that requests. And app2container, right, prepares your container for ECR. That's it. Well, still, Docker files are not that bad. And you can use only one slide to show the entire Docker file for the application. But still, there are a few interesting points. Like here, we use entry point and exec to run this application as a main process of the container. And it's possible because the base image is Alpine, and we don't exclude shell from there, and exec command is present in that shell. We also create a special user, and we bypass the lack of entropy thing. And we put a flag to elastically tune our heap according to what actual limit do we have in the container. And this number, like 80%, means that we understand that our non-heap memory will be utilized fine for this application, and we expect some known size of the pod at this time. Then we write this Docker file with this flag. So we do it manually because we know it. That's an important point. Another approach is to use Paketo Buildpacks, a project by Cloud Foundry Foundation, and you can build containers of your, like, for example, Spring Boot applications using a command line and standard set of plugins. It also can be used from the outside of your source code as a command line tool to prepare your code to be a container. And by the way, by default, Java Buildpack uses the Berica JDK. And there's a special build pack for Spring Boot, and there's a chain of dependency between build packs. So if you use Spring Boot build pack, it will use Java build pack to perform certain tasks. And it's very easy. If you look at any examples, samples from Spring Boot, for example, you'll see some settings related to that containerization functionality. And here you see some builders mentioned, and there's a property that regulates either you build a native image or you build a container based on classical JVM. During the process of build, here is a Maven build, you see that there are additional properties that can be tuned, and you can select the version of your JDK, etc. These are properties of this plugin that map to properties of the build pack to help you to tune things easily, slightly easier compared to what you have done if you set all the internal properties by hand. So the process then you build a build, then you use a build pack consists of the part then you perform the build, and you use the part of stack called build image, and then you run your container in the cloud or somewhere else. At runtime, you use some base image, and that's a base builder. It is a small image that doesn't contain your build tools. It makes sense because we all like smaller images, like Alpine, or here it is some distroless. Or, by the way, next week we release Paketo Cloud Platform, small images with Java based on Paketo Linux. Anyway, we finally start such a container built by a build pack, and you see we have some interesting options set for us automatically, and that means it really someone cared about the boilerplate. What does it mean? Well, first, how this magic happens. There is some script, Go script compiled as an executable that acts as a launcher for the JVM, and it finally determines the kind of tries to determine suitable flags for the JVM that you see during that log, based on what limits are provided for the container. So it does it in runtime, and then it starts the JVM. And in source code you can find also some tooling written in Ruby. I love this approach. Then you combine different languages to reach our final goal. And that behavior can be tuned by that flags that you saw in build log. Like, for example, you can tweak the so-called BPL JVM thread count. Well, that's actually a count related to the extra saved memory that's preserved then you calculate the final heap size. You preserve some memory to contain thread stacks. Why do you need like so much memory? Because you have Tomcat inside, and Tomcat creates a big thread pool, and each thread contains typically it occupies half of megabyte or a megabyte for its stack. That means you can require 250 megabytes of native memory just for Tomcat thread stacks. Well, that's important to know, right? Because you have to reserve that room. There may be also some extra headroom, and you of course load some classes, and it's better to know in advance how much classes will you need during the peak load of your application work to reserve that space for PEMGen. Also, there are regular JVM flags that you can provide there during in configuration for that plugin, and that flags also include active processor count flag. And someone might notice that in the log that count was set, but you can reset the default behavior by providing 0 for active processor count, or you can provide your own number if you realize what's best for your service. Well, and what's best for your service? Let's look at that. Oh yeah, first of all, small remark. In some earlier versions, there was a bug that actually caused your throughput dropping from 2000 requests per second to 500 requests per second just going into the container. And who might notice that if you just realized, if you just containerized our applications and no one measured the result? If no one measured the result in performance. The bug was about related to CPU number detection. So CPU number was almost always set to 4, even on a huge machines like machines with 64 CPUs. And that was a tremendous underutilization, especially compared to a regular JVM started in the very same environment. Well, if we imagine that we have built images using different approaches, we can look at their sizes. So first, the manually crafted Docker file gave us fully functional JDK and shell and the application running in a traditional manner, having the size of 142 megabytes. So the first line here is the base image. The second line is the image with the application. Then there are two build packs. The 17.4 megabytes is the runtime part, and builder is huge. It's 578 megabytes. You see the difference, why we don't have the same part for two purposes. And there are two images built using build packs. First one is it contains a native image, and it's 153 megabytes. You see it's slightly larger than the one with JVM derived from manual written Docker file. And there's also the one that's built for using JVM, and it's 229 megabytes. And still, you see it's much better than the one that you could produce by using some random or kind of well-known OpenJDK images. That would be around 500 megabytes. They're all much better than that. Well, what should we do with these containers? We are going to put some load on them and figure out what's the best configuration for their JVM flags and for their pod sizing. And it's not a trivial question. There are some services that try to do that automatically, but no one really succeeded yet in that interesting problem. Well, we'll select one of the endpoints that they have in the application, and we'll put some load and measure the latency to control our worst latency in the stable case. And we'll see what throughput we can squeeze out of such deployment. And we'll look at different configurations for our pod sizes and our JVM flags. Of course, pod sizes do not exist in vacuum. We often target some certain cloud specific one that has a granularity in its offering. Like here, we can imagine going into AWS, EC2, but it may be any other cloud. And it also depends on what kind of scaler do you use, because if you use more simplified automatic scaling, that even more limits your choice of available pod sizings, like you see here in this table. So first of all, let's start the application running, well, without any container. We'll just put a memory limit and we'll do some basic containerization by task set, but just to limit the number of CPUs on a big machine. And here you see that this application can be built as a native image, or it can be run as a general JVM application. And in this case, native image gives the better performance, and exact numbers are like 1,100, slightly more requests per second, and 2.4 thousand requests per second. And from an IF standpoint, I don't know the way to scale it more on this machine. I can give it more CPU or memory resource, but it doesn't work better. And it's a good case. That's what's typically happens with our applications. We don't know an easy way for vertical scaling, but we still have the resource. We have enough memory on this machine. We have enough CPUs. So we say, okay, let's run many instances of this application and this hardware. And let's balance the requests between them and try to get better performance, right? Well, okay. First, as I said, then we put a load on application, it warms up. So first it responds very slowly, and then it becomes much better. And to tune the application, we'll measure the stable part of its work, and we'll look at the latency there to keep it at a certain level of 100 milliseconds. The less is the better. So then we put that instance in just one container. We keep the same memory limit and we try to measure what happens. And you see there's a drop in performance just because of we used a container. So that's not so good. But it's good to know. It's not a dramatic drop, but it's visible. It's around 5% or so. Then we create a cluster of a single node, and this node contains a pod, and we also have an ingress to address that single node, but we still keep the same limit. And you see the performance dropped really badly. And it's good to know what happens there. Especially you can try it with the ingress or without it, but it's still the same result. So we have to scale that works really worse than what we started from originally. Well, let's increase the number of pods and let's make them slightly less. We'll use lesser pods, like here it's 8 CPUs and 16 gigabytes. or we can try just to replicate what we have, to use more ports of the same size. Anyway, we can see that we have restored our original performance by using more ports, and it's very good. And what else we can observe is the CPU utilization during the start of our application and CPU utilization under the load. Well, it's relatively easy, of course. Okay, let's create even more of ports that are even less themselves. Great. Let's create 16 ports using the same entire resources that they have. And finally, we beat the initial performance. We have more than 2,200 requests per second, and we still have a good latency under 100 milliseconds for the 100 percentile. We limit CPU usage exactly by putting the flag, but I might actually just provide active processor count 0, and this scaling works similarly for both kinds of build packs that I try to build, for manually built one and for the one built by the Paketo Buildpacks, right? We see the same numbers. So we scaled out applications, we just have different sizes of containers. And of course, we probably prefer the more effective one, or we might prefer a more simple one to create, right? Okay, let's go below 1 CPU as a limit, right? Let's provide very small, like small, not very small, but small heap limitation here, and 1/2 of the CPU. Well, you still see about the same performance. It's actually slightly lower. So we also had different GC because our ergonomics, they have just switched. And if you haven't noticed that by logging or by monitoring, that might be bad for you, right? Because you can still enforce the type of your garbage collector and have a better performance. And the surprise, we can do the same for the native image and to reach 500 requests per second for this particular application. So we just changed the configuration and improved performance more than twice. Yeah, and we can again go to very fractional tiny pods, but that won't bring us real benefits. All right, so we scaled our applications, but we have to work for it, right? Remember of that. Developers have to work to squeeze the most effective performance from your application for the certain amount of money. And that's also related to the testing. Performance work is related to testing, and we have to deal with dependencies. Developers have to measure performance, and you have to replicate your production environment for that purpose. You have to analyze how your memory is used. You have to be careful about the most important sources of waste in native memory and most important sources of waste in your CPU. You have to distinguish between CPU and startup, CPU and warming up your application, and what happens on the stable part of its lifetime. Few options that are set by the launcher in the build packs are actually the useful ones, so keep an eye on them. You can always try to enhance the behavior of your JVM by using some combined ergonomic switches or some extra things like AppCDS for the better startup. You can select smaller container images based on Paketo Linux or Alpine Linux and Libericalite. They're quite convenient. Don't forget about all the magical tools that can help you to bring your application to the cloud. Also remember about technical details, like the memory consumed by Fargate on your pods. So you have certain difference between the limit that you have and what your Java application can use. Please monitor your applications and analyze your logs or install APMs. They really help us to get useful statistics out of working productions. And I say again, involve developers into cost optimization route. Thank you very much.